And we see that we see that in our blood system too. We see that here in our aorta and arteries we have a very high pressure, and then we have a relatively low pressure in our capillaries. So there's going to be flow. There's going to be flow from our arteries to our capillaries, right? It doesn't go from our capillaries to our arteries. It goes from our arteries to our capillaries because there's a pressure difference. And once again, there's a pressure difference between our capillaries and our veins here. So that difference in pressure will create flow, right? Our blood doesn't go from our veins to our capillaries, in part because there's this pressure difference. This pressure gradient is telling the blood to go in a certain direction. So that's one way we get flow in a unidirectional way, is because we have a gradient of pressure starting from our aorta all the way back to our veins, to our superior and inferior vena cava. Okay, we have other mechanics to go over. We have to make an assumption for this one. That blood is incompressible. I'm just going to put that out there, and it won't make too much sense right now, but it will make sense at the end of the slide, hopefully. So we have, let's say we have 5 liters here, right? And we're going to push it in at the rate of 1 second. We push it in here, put 5 liters of fluid in at a rate of 5 liters per second, right? Just shove it in there, right? How much do you expect to come out of this tube? 5 liters per second, right? That makes sense. Whatever goes in comes out, right? The reason we can expect that is because none of that fluid is being destroyed, none of that fluid is being created inside that tube, right? If that was, you could expect something different to come out. But the fact that you're conserving your fluid, there's no fluid destroyed, no fluid created, you can expect whatever goes in comes out, right? And the idea of blood is not incompressible, right? There's no compression happening here. So you can expect whatever's going in is coming out at the same volume, right? So let's look at this bottom case here, right? If you have 5 liters per second going into here, what's coming out? Is it 5 liters per second?
Yes.
Not quite. Well, sorry, yes. Aha! 5 liters per second still coming out. 5 liters per second still coming out, right? But there's something different here. What's different here?
Coming out slowly.
Yeah, but let's back up. What's different at causing that?
The wider opening.
It's a wider opening, right? So these are talking about flows. These are volumetric flows here. This is nothing about the speed of the flow. So what's the velocity of this flow? Right? Velocity here is going to be the same as velocity here. These are equal because the openings are the same size here, right? But velocity 1 here is not going to equal velocity 2 here. Well, maybe I'm making 3 different values. So let's say velocity 4 here is not going to be the same as velocity 3 here because they have different openings, right? The volumetric flow is the same, but the velocity is different. And that is because of this special equation. The velocity v equals the volumetric rate, q is volumetric rate, over the surface area. And so this circle here is representing the surface area, this circle here is representing the surface area here. And so what's happening here is because, the surface area here is greater here, as A increases, our velocity is going to decrease here. This will lead to a velocity decrease. And hopefully this makes sense. If you keep your volume the same, but you changed your area, the velocity has to get slower. Let's think of an intuitive case. You have a hose, right? Spewing out water, right? You cover a part of that opening. What happens to the water speed? It comes out faster, right? That's just you doing this equation. And I can prove it to you mathematically. People say, ew, math, but it'll make sense. Okay, so you have your rate, you have your area, right? If this goes down, so you have Q over something small, that's going to equal something big, right? It's fuzzy math, but it's still math, right? So all you're doing with the hose, right? You had some area, and then you're closing up. You're making that area smaller by closing part of it up, and because of that, water's shooting out faster. It's really geometry. It's all because the idea is blood is incompressible, fluids are incompressible, and assuming you're not creating or destroying any fluid in the process, it has to come out at the same rate, right? The volumetric rate is conserved, so it has to come out faster to basically be the same. Hopefully this makes sense to you. This is probably the hardest concept to get a hold of, this whole equation here. If you're struggling with this, there's a good chance to come to office hours, talk to me afterwards, something like that. But hopefully this makes sense to you. Yeah. SA is surface area, sorry.
And Q is just the volumetric rate?
Mm-hmm.
What's velocity?
The velocity is how fast that fluid is moving in a given direction. So the volumetric rate is how much volume is moving, but that doesn't actually tell you how fast it's moving. Like if you put a ruler there and you saw the fluid move past that ruler and you timed how fast it moved it, that's velocity. That's different than volumetric rate. Okay. So this is actually going to be pretty important when you get to capillaries. So just tuck this information away. We're not going to see it right away. We'll see it later when we get to talk about capillaries. All right, we're going to talk about resistance now. So there is another principle we are going to play with. This is called, this is such a hard name to say, French name, Poiseuille's law. Poiseuille's law says resistance is proportional to viscosity. So we're going to represent this kind of fancy N with viscosity. It's also directly proportional to length. And it's inversely proportional to the radius of the tube, power 4. So this is Poiseuille's law. And so when you're talking about resistance, it's like resistance when we're talking about electrical charge. It is basically the resistance that opposes flow. So the higher the resistance, the less flow you're going to get. That's what resistance is here too. And when you have fluid flowing through a tube, the resistance is caused mostly by the friction that's caused between the fluid rubbing against the surface of the tube, right? Just think about you kind of sliding against the floor. The resistance of you sliding across the floor is the friction between you and the floor, right? That's the same kind of friction that's happening between this fluid and the sides of this tube, right? And so that's the main place where you're going to get resistance. There's other places, but for now let's just consider that as the main source of resistance. And so what this is telling us is viscosity is directly proportional to resistance, meaning the stickier something is. So viscosity is how sticky, how thick something is. So a good example of something that's really viscous is honey. Honey is really viscous, or molasses is really viscous. If you kind of pour it onto your food, it just kind of eeps out, like really slowly, right? Something that's not very viscous, something like alcohol, like 100% ethanol. If you ever poured it, it pours really easily. It's really thin in your finger. If you ever felt it on your fingers, it feels really thin, right? Or acetone is another example. Even water is kind of very low viscosity, right? But very, very different than honey, right, or molasses. So viscosity can be directed to resistance. We're talking about viscosity to the fluid. So if your blood's like honey, it's going to have a lot of resistance to flow, right? It's not going to flow very well if it's all sticky and it sticks to stuff and it kind of sticks to itself, right? So that makes sense. The higher the viscosity, the higher resistance. The length of the tube kind of makes sense too. If you have a longer tube, so in this example, If you have a long tube, that's more surface area for the fluid to interact with, right? More surface area to interact with, more friction, more resistance. So I hope that makes sense, right? The more tube you have to go through, the more length of that tube, the more resistance is going to be. Now, resistance is inversely proportional to resistance. Meaning if one goes up, the other one goes down. That's what inverse proportionality means.
You just said resistance is inversely proportional to resistance.
I did, I'm sorry. Resistance is inversely proportional to radius of the tube. Sorry. Thank you for catching me. All these recordings won't make much sense afterwards. So this is less intuitive, but this also gets to the idea of more surface area. If your radius of your tube is smaller, there is more surface area to volume. So I'll write that out. Below, R gets you high surface area to volume. Now, I'm not going to explain that much more than that. The inverse is also true. High radius gets you a low surface area to volume ratio. But the idea is when your tube has a low radius, there's more surface area for that volume to interact with. More surface area means more what? More resistance means more friction, which leads to more resistance, right? So that's why the radius is inversely proportional and has this power to the 4. So that means